Welcome to Lecture 3 of our Microeconomic Analysis 1 course with me, Dr. Craig Webb. In today's lecture, we will be looking at elasticities, a very useful and widely used concept in economics. We'll give the definition of elasticities in various forms and get to grips with handling them. And then we will look at a taxation problem and show how a little knowledge of elasticities and a bit of mathematical analysis can yield great insights into a complicated problem. So let's start with a basic recap of some of the terms we'll use today. When we talk about the quantity demanded for a good, we're talking about the amount of a good that a consumer is willing to buy at a given price. A demand function describes the mathematical relationship between quantities demanded and the price of that good, and also of other factors. So typically in microeconomics, we assume a demand function that depends on the prices of the good in question, but also depends on the prices of other goods, and may also depend on the consumer's income, and possibly other factors. Now, when we draw a diagram of a demand function, we normally just represent demand as a function of a good's own price. And when we do this, we're really just thinking, well, let's imagine that all other factors, whatever they are being held constant. And then we can examine how a consumer's demand changes as the price of that good in particular changes. Also remember that when we do draw diagrams of demand functions, it's conventional to put price on the vertical axis and quantity on the horizontal axis, as if price depends on quantity, which seems the wrong way round. So really we're drawing what we call an inverse demand function, price as a function of demand, even though we actually think of demand as a function of price. So let's talk about elasticity. It's a very important idea in economics. What does it mean? Well, intuitively, elasticity indicates how responsive any variable is to a change in another variable. So that's the intuition, but how might we measure this? Well, one way of measuring elasticity is to take the percentage change in one variable and divide it by the percentage change in another variable. Why do we use percentage here? Well, if we were to just use pounds, for instance, an increase of £1 is the same as an increase of €1.14, and this is the same as an increase of $1.23. So it quickly gets problematic if we want to compare the responsiveness of different goods to price changes across the world. So we use percentage change as a kind of universal currency. So let's give a definition of our measure of elasticity. And this is a mathematical definition. We're going to state it very general, just for a variable z, which is a function of some variables x and y. We can define the elasticity, capital E, of z with respect to x. So we say elasticity of z with respect to x is the percentage change in z divided by the percentage change in x. Now here we've used the notation. This triangle is a capital Greek delta, which we use to denote change. So it doesn't need to be a small change like a derivative. Essentially, change just means the new value minus the old value. So if we take delta z divided by z, we get the proportional change in z. If we multiply that by 100, we get the percentage change. The same for x as well. So for instance, if we say the elasticity of z with respect to x is equal to 3, then what we mean is a 1% change in the variable x causes a 3% change in the variable z. Now, the definition I've just given of elasticity as the proportional change of z divided by the proportional change of x. It's often more convenient when we're working on theoretical work to work with derivatives. So we can imagine this change becoming infinitesimally small, essentially this capital delta approaching zero. And then we can define elasticity at a point. Sometimes the definition I gave previously is called arc elasticity, where the arc refers to the fact that we're connecting 2 points, the new point and the old point. And we want to calculate elasticity at a given point. So here is the definition of point elasticity. If we rearrange the definition above of elasticity, we get change in z over change in x multiplied by x over z. So if we replace this change term with a partial derivative, we can define the point elasticity, which we will denote epsilon, equal to the partial derivative of z with respect to x multiplied by a ratio x divided by z. Okay? So the partial derivative, remember, is essentially a derivative where we're assuming that every other variable, in this case the variable y, is being held constant, and we're just differentiating z with respect to x. And the ratio x divided by z is doing the job of removing the local currency, so we're expressing in proportional or percentage terms. So this is our basic definition of point elasticity. Epsilon equals the partial derivative of z with respect to x multiplied by x divided by z. So to get to grips with this definition, here's a nice exercise. Let's prove the following result, that our definition is equivalent to the following. So you're asked to prove that epsilon is also equal to the partial derivative of the log of z with respect to the log of x. So have a go at this exercise, go through the definition, and pause the video now, and in a moment I will show you two different proofs of this result. Okay, so we've been asked to prove that the elasticity of z with respect to x is equal to, so let's just recap, the elasticity of z with respect to x, which we denoted epsilon. The point elasticity is the partial derivative of z with respect to x multiplied by x over z. Okay? And we've been asked to show that this is equal to the partial derivative of the log of z with respect to the log of x. So the first proof I'll show you, it will feel like I'm cheating, because I'm going to bring in a new concept called a differential. And the formula for a differential, essentially we use a d to denote the change in z, and then the formula is that the change in z is equal to how much does x change z, or that would be the partial derivative of z with respect to x, multiplied by how much x changes. So this is essentially saying a small change in x. How does that change z? Well, we take that small change in x, multiply it by the rate at which it changes z, and that gives you the change in z. And this is called a differential. So if we use this formula, we can see that the differential of log z, here we would have the partial derivative of log z with respect to z, for instance, would be let's just write that out. The partial derivative of log z with respect to z multiplied by dz. Okay? So this is just using the definition of a differential. Then we know how to differentiate logs, so this would be 1 over z dz. Okay? So the differential of log z is equal to 1 over z times by dz. Okay? If we do the same for x, d log x, that would be 1 divided by x dx. Okay, now here's the cheating part. I'm essentially going to divide these two and say d log z divided by d log x. Okay, and then call this the derivative of log z with respect to log x. Now I know these derivatives, typically dy over dx. It's not a fraction. Okay, so you can't normally do that, but you are allowed to do this with differentials. But I see that it feels like cheating, so I'll show you a kind of better proof in a moment. But let's just follow this argument through. So we know d log z is 1 over z times by dz, and d log of x is 1 over x dx. So dividing these two, we get x over z and dz dx. So this is our formula for the elasticity of z with respect to x being the same as the derivative of log z with respect to log x. Okay, so there's the first proof in inverted commas, because I brought in a technique we haven't seen before. Let me show you another proof where we're going to use the chain rule. Okay, so now we will do, let's call this proof 2. And remember, what we're proving is that the elasticity of z with respect to x, the point elasticity of z with respect to x, is simply the partial derivative of the log of z with respect to the log of x. So now I'm going to do what we call a change of variable. So let's say let x with a curly hat on, this is called x tilde. So let x tilde be log of x. Okay, and we'll let z tilde denote log of z. Okay, so we've got two new variables, x tilde and z tilde. What do we know about these? Let's see. Well, we know, for instance, that the partial derivative of z tilde with respect to z is simply 1 over z. That follows from the rules for differentiating logarithms. We also know here, now if I invert this formula, we know that if x tilde is log of x, then I know that x is equal to e to the power x tilde, right? Because this exponential is the inverse of the logarithmic function, the natural log. Okay? So I know that the partial derivative of x with respect to x tilde, the derivative of e to the x tilde is just e to x tilde, which equals x. Okay? So now let's attempt this formula for the partial derivative of log z with respect to log of x. And using our change of variable, this is the partial derivative of z tilde with respect to x tilde. Okay, so that's just renaming the variables. Now I'm going to use the chain rule, which is going to be our best friend. Okay, I'm going to form a chain. If I want to partially differentiate z tilde with respect to x tilde, I could form a chain as follows. So I could partially differentiate z tilde with respect to z, and then I could partially differentiate z with respect to x, and then I could partially differentiate with respect to x tilde. Okay, now you can see the chain here. Essentially, I want to partially differentiate z tilde with respect to x tilde. So I've gone, well, how does z change x tilde? How does x change z? And how does x tilde change x? Okay, and you can form very long chains using the chain rule. Okay, so what do we know about these? Well, we've already established that this first term is simply 1 over z. This partial derivative here we'll just leave alone, so we'll leave that as the partial derivative of z with respect to x. What about this last term? We already know that the partial derivative of x with respect to x tilde is e to the x tilde, which equals x. Okay, so here we just have x. So just cleaning up slightly, this logarithmic derivative, the derivative of log z with respect to log x, is equal to the partial derivative of z with respect to x multiplied by x divided by z, which is precisely the point elasticity of z with respect to x. Okay, so from this point on, as this course is more of a mathematical nature, whenever we refer to elasticity, really we will be talking about point elasticity, and we'll just stop saying point elasticity and say elasticity from now on. Okay, so that's the general definition, and now let's give some very commonly used ways in which this concept is used in economics. Of course, the most used is the following term, price elasticity of demand. Really, when we say price elasticity of demand, we are meaning the elasticity of demand with respect to price. But price elasticity of demand, or PED, is the common way of saying this. So let's suppose we have a demand function. Q is a function of price or possibly other variables. The price elasticity demand is, and we'll denote this epsilon, is essentially the point elasticity of demand with respect to price. So the partial derivative of demand with respect to price multiplied by this ratio price divided by quantity demanded. Typically, we'll imagine that this is a negative number because we expect, or we haven't shown yet, but we typically expect that as the price increases for a good, demand goes down. This doesn't always happen, but it's very, very common. So we'll often think of this as a negative number. And there's some common names to distinguish between different cases. So we will say demand is price elastic if this epsilon is less than -1, so in absolute terms it's a bigger number than 1, it's more negative than -1. And what does this mean? This means that if the price goes down by a certain percent, demand goes up by a greater percent. So demand responds a lot to changes in price. Okay? Some other commonly used terms in the kind of elastic camp are unit elastic, which refers to the case where epsilon is precisely equal to -1, and also a term called perfectly elastic, which is where epsilon is -infinity, which is clearly a limiting case. It's not perfectly realistic, but it turns out to be useful in certain circumstances. Essentially, it means if the price of a good goes up at all, you simply stop buying it. Now, that turns out to be quite a useful assumption when we study competitive markets. If there's lots of firms selling a good and one firm tries to raise the price, everyone will stop buying that product from that firm. So it's not entirely without use. Another term often used is inelastic, which means that the demand for the way demand responds to price is less than proportional. So if epsilon is negative, so it's less than or equal to 0, but it's larger than -1. It's greater than -1. So, for instance, -0.5 would lie in this inelastic camp. Perfectly inelastic is the case where epsilon is simply 0. So what would that mean? Well, it means if the price of a good changes and elasticity of demand is perfectly inelastic, then the consumer still buys exactly the same amount. The demand has not responded in any way to the change in price. Of course, this equal to 0 case is unrealistic, but there are well-known examples of inelastic goods. Common ones include tobacco and petrol. So things like tobacco and petrol, which either through addiction or just through necessity, people have to buy the same amount of them frequently. If the price changes, their demand does not change as much as the price. So they're the classic examples of goods with inelastic price elasticity of demand. So let's do a quick example of calculating elasticity, and let's use the simple linear demand function. Linear demand. In which case we're going to suppose that quantity demanded is equal to some constant A minus some constant B multiplied by the price. And here we're imagining that A and B are both positive numbers, so this demand function satisfies the law of demand. It's a downward sloping function. Okay, now elasticity, so far we've been defining it using partial derivatives. So for instance, the elasticity, we would write it as the partial derivative of Q with respect to P multiplied by P over Q. Okay, now in this case, Q, demand, is a function of just a single variable price. So it's better really to just write the elasticity as a normal derivative. So the derivative of Q with respect to price multiplied by P over Q. Okay. In general, we use this notation, partial derivatives, when the function depends on several variables. If it's a single variable, then it's better to use this notation. And you'll see why this is the case more so in your mathematics courses. Okay, so let's calculate this elasticity term here. Well, the derivative of Q with respect to P is simply this constant slope term minus B. So the elasticity here is this derivative minus B multiplied by P and divided by Q. So we can see here that the elasticity depends on the price and quantity. And let's have a look at the diagram. So in this diagram, now I can tell by looking at this diagram, the demand function intercepts the axis at 12 on both axes. So this seems to be the case where A equals 12 and B equals 1. And in that case, you can actually calculate some numbers quite simply. So for instance, when the price is 9, we can use the formula allowing A equals 12 and B equals 1 to determine that the quantity is 3. Quantity demanded is 3. And so using our formula for elasticity, the elasticity will be minus B is 1, so minus the price divided by the quantity, which is minus 3. To do one other example, when the price is 6, demand is also 6, and so elasticity is minus 1. So even though the linear demand function is very simple, point elasticity of demand is changing everywhere along this demand curve. While the linear specification of demand seems to be the most simple, we've seen that price elasticity of demand for linear demand functions, that price elasticity varies at every point along the demand curve. It's always changing. Now, this may be appropriate, but if you're looking at a particular industry where you have reason to believe elasticity is a more stable defining feature, then the following parametric form of a demand function is very, very useful. So this is called the constant elasticity of demand function. Really, it's a family of functions. So it's demand capital Q is equal to some constant capital A, which is a positive, multiplied by price to the power epsilon. Now, we've already used epsilon to denote price elasticity of demand, so we need to make sure that our use of epsilon here is indeed appropriate. So we'll prove this as an exercise. So let me just first mention that this particular parametric form of demand function, it's really a family of demand functions. You can see in the diagram here different demand functions depending on that parameter epsilon. So epsilon equals 0 is the perfectly inelastic case where the inverse demand function is perfectly vertical. In that case, demand never changes as the price changes. And the perfectly elastic case, epsilon equal to minus infinity, is where inverse demand is perfectly horizontal. So in that case, if price changes even slightly, you stop buying the good altogether. And in between, we have the whole range of different values of epsilon, giving you different demand functions. Okay, so this is the family of constant elasticity of demand functions. And as an exercise, I'm going to ask you to prove that our use of the epsilon notation here is appropriate. So prove that the above form of demand exhibits constant price elasticity of demand. When I say constant, I mean the price elasticity of demand is not a function of price or of quantity, it's simply a number. Now you have two different and equivalent definitions of elasticity so far. We had elasticity as the partial derivative of demand with respect to price multiplied by the price divided by quantity ratio. And we also had an equivalent definition, which was the derivative of the log of demand with respect to the log of price. Use either of these or both of these and have a go at proving this exercise. Pause the tape here and then I will give the proof in a moment. Okay, so let's prove that the constant elasticity of demand function really does exhibit constant elasticity. So let's just write demand Q is equal to some constant A multiplied by the price to some power epsilon. And we're going to show that the price elasticity of demand for this demand function is simply equal to epsilon. It's a constant, it's a number, it doesn't depend on P or Q. So I'm going to give two proofs here. So let's write proof 1. In proof 1, we'll just prove from first principles. So if you remember the formula for price elasticity of demand, what do we mean by this? Well, this is a demand function is a function of a single variable. Okay, so I'll just use the first derivative of Q with respect to P and then multiply that by P over Q. Okay, so this is the formula for price elasticity of demand. And let's work through each of these terms. The first derivative of Q with respect to P is equal to, so applying the standard rules for differentiation, the power epsilon comes down, and then I deduct 1 from the power on P. So the first derivative is capital A multiplied by epsilon multiplied by price P to the power epsilon minus 1. Okay? So let's see what happens when we plug this into our elasticity formula. So dq dp multiplied by P over Q is equal to, so this term here, A epsilon P to the power epsilon minus 1, multiplied by P again and divided by Q. Okay? Now here I've got P multiplied by itself epsilon minus 1 times and then multiplied by itself again. So clearly, just using standard rules of indices, this is P to the power epsilon divided by Q. Now at this point, it doesn't look too hopeful because our elasticity formula still has P in it and it still has Q in it. But remember that this Q is equal to A times P to the power epsilon. Okay, so let's replace that. So this is equal to A times epsilon P to the power epsilon, all divided by Q, which is equal to A times P to the power epsilon. And now we can cancel out the common terms. We've got A divided by A, P to the power epsilon divided by P to the power epsilon. And we see that this elasticity term is simply equal to epsilon, which is precisely what we needed to prove. Okay, so this is a constant, this demand function exhibits constant elasticity of demand. Okay, now let's give another proof where here we're going to capitalize on some work we did already. If you remember from earlier in the lecture, that price elasticity of demand is also equal to the derivative of log of Q with respect to log of P. Okay? Now we've already proved that. We used partial differentiation notation, but here we have a single variable, so this is the appropriate formula. Now, let's take logarithms of this. We have log of Q is equal to log of A times P to the power epsilon. And then using the basic rules of logarithms, this is log of A plus epsilon times log of P. Okay, so just recap them rules of logarithms if this looks mysterious. Now, if I want to evaluate this derivative, I'm saying what is the slope term here? This is what we call a log linear function. Log of A is just a constant, and then we have some constant slope term epsilon multiplying log P. So if I take this derivative here, clearly this is simply epsilon. Okay? So that would be a second way of proving it. And the nice thing here is that we're building on results that we've already proved. Price elasticity of demand is perhaps the most commonly discussed form of elasticity in economics. In fact, if you hear an economist simply refer to elasticity, they probably mean price elasticity of demand. But there are other types of elasticities that you will come across. So here are some examples. Let us just recall quickly the basic definition of the price elasticity of demand for a good X1, which we denoted epsilon, which is the partial derivative of the demand for good 1 with respect to that good's price, multiplied by the price over quantity ratio. Another form of elasticity is called cross-price elasticity of demand for X1. So here we can envisage another good, let's call it X2, which has a price P2, and discuss the elasticity or the responsiveness of the demand for good 1 with respect to changes in good 2's price. Okay, so formally this cross-price elasticity would be the partial derivative of the demand for good 1 with respect to the price of good 2 multiplied by the price of good 2 divided by the demand for good 1. Now, whereas we expect price elasticity of demand to be negative, I suppose this cross-price elasticity need not be negative. For instance, if the goods were substitutes, substitutes, if the price of one good goes up, you may buy less of it, you may buy more of its substitute. Okay? In which case this number would be positive. If the goods were complements, so things you typically buy together, then if the price of good 2 was to go down, so you buy more of good 2, you may also buy more of good 1, so you would expect this cross-price elasticity to be negative. So it's not necessarily negative, and it indicates whether the goods are substitutes or complements. Another type of elasticity is called income elasticity of demand for a good. So in this case, we could say the elasticity of good 1 with respect to income defined as the partial derivative of demand for good 1 with respect to income, and then multiply it by our ratio income divided by the demand for good 1. So this tells us the responsiveness of your demand for that good as your income increases by a certain percent. As well as the various forms of elasticity of demand, we can apply the notion of elasticity very naturally to supply functions. So elasticity of supply captures the responsiveness of the quantity supplied to various variables. So for instance, we could talk about the price elasticity of supply, and we denote this by the Greek letter eta, which would be the partial derivative of a supply function with respect to price, multiplied by this price divided by quantity supplied ratio. We would expect this to be a positive number, and to interpret it, if eta was equal to 2, for instance, then we might expect a 1% increase in the goods price to stimulate a 2% increase in the goods supply. If the supply curve is upward sloping, then the price elasticity of supply will be a strictly positive number. And if it's downward sloping, which would be rare, but it can happen, we would see a negative price elasticity of supply. As with price elasticity of demand, we can distinguish between various cases for the sake of terminology. So we will say that supply is elastic if this eta is greater than or equal to 1. And this means that if the price of a good increases by a certain percent, then the firms want to supply, the way they respond is by increasing their supply by an even greater percent. Unit elastic is the special case where eta equals 1, and perfectly elastic is the case where eta equals infinity. Again, this equals infinity case seems unrealistic, but you can well imagine the intuition of a firm that sees the price rise slightly and then wants to supply as much as possible. So it can be a useful assumption. Inelastic supply refers to the case where eta is greater than or equal to 0, but is less than 1. So this means if the price increases by a certain percent, supply increases, but by not such a great amount. So supply does not respond to price as much in a proportionate sense. To look at the boundary case, perfectly inelastic eta equals 0 would be the case where even as the price changes, the firm supplies exactly the same quantity to the market. Very similar to the constant elasticity of demand function, there is a well-known constant elasticity of supply function, which is the following parametric form, where Q, the quantity supplied, is equal to capital B, which is some positive constant, multiplied by price to the power eta. Again, we should check that our use of the letter eta is appropriate here by proving that the price elasticity of supply is constant, is just a number, and is equal to this eta used in our notation here. The proof is entirely similar to the constant elasticity of demand case, so I won't go through it now, but I encourage you just to double check this. The constant elasticity of supply function is really a family of functions. So looking at the diagram here, we see various cases for different values of eta. So if eta equals 0, in this diagram, supply is perfectly vertical. This is the perfectly inelastic supply. The firm supplies the same amount for every price level. And if eta is infinity, then the supply is perfectly horizontal. In between, we see the more realistic cases. So the unit elastic case here is a linear function, and the functions are convex for inelastic supply functions and concave in this diagram for the elastic functions. It's worth bearing in mind that demand and supply elasticities, they may be stable features of a product in a given industry. However, they may well vary over time. So these short-run demand or supply elasticities may well differ from long-run elasticities. To see the intuition for this, you could imagine that if a firm is unable in the short run to respond to a price increase, simply they don't have the capacity at hand to manufacture a lot more of a given good, then we may well see that short run elasticity of supply looks more inelastic than long run elasticity of supply. And there are several factors that would determine this. For instance, ease of substitution, the storage opportunities, and so on. We're going to close the lecture by giving an application to show how useful the idea of elasticities can be. Now, there are many, many uses, and you will see these throughout your economics training. But we'll start with a simple example based on a tax problem. So when analysing competitive markets, remember from our last lecture that we look at equilibrium prices. Now, these are magic things. An equilibrium price is a price such that the demand for the good equals the supply of the good. So there is no excess demand and there is no excess supply. This single price kind of perfectly organises the market and there is no waste. So another way of saying this is that a price P is an equilibrium price if the demand as a function of P is equal to the supply, which we can think of as a function of P as well. Okay, so let's now consider the effect of imposing a tax on suppliers. Now, politically, this is really a popular suggestion. Clearly, corporations make a lot more money than the average consumer, and the idea of taxing very large companies has a lot of political weight. But let's think about this further and ask an important question. Even if we aim the tax at suppliers directly, and we say to suppliers, for every unit you sell, you must pay us some tax, who really ends up paying this tax? It turns out elasticity is going to play a big role in helping us answer this question. Now, if the firm only receives P minus T for each good, which means we're taxing the firm directly for every unit they sell, well, in that case, how much are they willing to supply when the market price is P? Well, they only receive P minus T for each good. So that's the amount that they will plug into their supply function. That will give them the profit maximizing a quantity to supply to the market when the price is P. They use P minus T in the function. So our equilibrium condition changes. Now, once we introduce this tax, the price that currently exists in the market may no longer be in equilibrium, and will only be in equilibrium if the demand equals supply, taking into account this tax. So demand, which is a function of price, which may be affected by this tax, will equal the supply from the firm who received the price but have to pay the tax. Okay, so this is our condition for an equilibrium. Let's move over to paper now and analyze this in more detail to see what we can say about it. Okay, so before we start analysing this tax problem, I'd just like to go over a kind of basic mathematical idea because it's going to be very important for what we do next. So this is on the difference between an equation, which I'm sure we've all heard of, versus what's called an identity. Okay. So let me just give you an example. So an example of an equation, a very simple one, could be x squared equals 9. Okay. And hopefully you can immediately tell me that x is either equal to 3 or x is equal to minus 3. Okay. So this equation implies that x has one of these two values. This is not true for all x, it's true for some specific values of x. So that's what we would call an equation. Okay, now there's lots of things we could do to an equation. We could add the same thing to both sides. We could multiply both sides by a positive number or a negative number, and it doesn't change the result. We could take logarithms of both sides, and this wouldn't change the result either. Okay, so what about differentiation? Can we differentiate both sides of this equation, and will it still make sense? Well, let's just check. If we differentiate x squared, we get 2x, and if we differentiate 9, which is just a number with respect to x, we just get 0. Okay, and of course 2x does not equal 0, because x is either 3 or minus 3. So differentiating both sides of this equation led to, it broke the equation. So just remember that if we have an equation, we can't just differentiate both sides of it. However, identities are essentially equations that are true for all x. So let me think of an example. If I said x squared is equal to, and then I said, well, it's equal to x squared, and I could add 4 times x and deduct 4x, okay? Now here, it doesn't matter what value x is. This is just universally true for all values of x, okay? So this is what we mean by an identity. It's like an equation that's true for all values of x. Sometimes they write it's written with 3 horizontal lines rather than just 2. But very often it's just written as an equation, and then you'll make an annotation, something like for all x. Okay. And now if we have an identity, let's try differentiating both sides of this. If I differentiate x squared, I get 2x. And if I differentiate this side with respect to x, I get 2x plus 4 minus 4. Okay, and these are still equal to each other. Okay, so that's the kind of message in brief, that if we have an equation, something that's true for some specific x, you can't just differentiate both sides of an equation. If you have an identity, so two sides of the equal sign are true, it holds for all values of x, then we can differentiate both sides of an identity. Okay, now let's look at our tax problem. We've started with this idea that the demand in equilibrium, let me just write this out. We've started with this condition. We've said, well, in equilibrium, whatever the tax rate is and the price, if it's an equilibrium, then supply equals demand. Okay, so we're going to treat this as an equilibrium identity. It's always true if we're in equilibrium. Okay, so now we're treating this as an identity. like staying within the equilibrium world, we can differentiate both sides of this, and it's perfectly okay to do this. Okay, so in this case, we could differentiate the demand with respect to T and the supply with respect to T. Okay, so we're differentiating. How does this demand change as the tax changes? How does supply change as the tax changes? And implicitly, we're saying, well, also the price will be changing to maintain this equation or this identity, so that these two are this is still true. Okay, so let's analyze this term a bit more. So here we've got the derivative of demand with respect to tax. So we could notice here we have kind of a function of a function. So demand depends on the price, which implicitly through this equilibrium identity depends on the tax as well. So we could write the change in demand as price changes multiplied by the derivative of price with respect to the tax. Okay, so that's simply using the chain rule to know that these two things are equal to each other. What about this side here? Well, here we've got P minus T. So I could write this as, for example, the derivative of supply with respect to, and then put P minus T here, and then the derivative of P minus T with respect to the tax T. Okay? And I can clean this up a little bit and write the derivative of P minus T here. And then in brackets, I would have the derivative of price with respect to the tax minus, and then the derivative of the tax with respect to itself, which would just be 1. Okay? Now, in the book, this isn't made entirely clear. So I think the easiest way to do the next step is the following, just to say, well, let's consider small taxes. Okay, so we're only going to be talking about small taxes, and our equations are only going to be approximately true. So P minus T, okay, if the tax is very small, it's very close to, it's close to P, okay? In which case we could say, well, for small taxes, this derivative here is approximately equal to this derivative, the derivative of supply with respect to price. Now, in the book, he says this is always true. When I say always, I mean for any tax, however large the tax is. This is always true if demand, or if supply, apologies, is linear, because there the slope term is constant. For nonlinear supply, it's approximately true, provided that the tax is small. Okay? In which case, so we're going to take it as true and say that our result holds for small changes in the small tax levels, in which case we can rewrite our equation, the derivative of demand with respect to price multiplied by the derivative of price with respect to tax is equal to, and then I'm going to replace this term here with the derivative of supply with respect to price minus 1. Okay, so this is an approximate equation that's a very, very, very good approximation when the tax is small, or if supply is linear, then it's exactly true. Okay, so from here, what we want to do is essentially get this derivative of the equilibrium price with respect to the tax rate. We want to get that by itself. Okay, so if we do some rearranging, let me just rewrite where we're up to, the derivative of demand with respect to price multiplied by the derivative of price with respect to tax is equal to, approximately, the first derivative of the supply function with respect to the price multiplied by derivative of the equilibrium price with respect to tax minus 1. Okay, now if we do some rearranging here, we essentially want to get this term by itself. Okay, now I won't go through all the steps, but I encourage you to try it at least once. You'll find that this derivative here is equal to the derivative of supply with respect to price divided by the derivative of supply with respect to price minus the derivative of demand with respect to price. Okay? So now we've isolated this term, which is precisely what we were hoping to do. I'm going to do one more trick, and that is to say, well, this almost looks like an elasticity formula, apart from the fact that we would like to multiply it by P and divide it by Q. And if I'm doing this to the top of a fraction, then I should do it to all the terms on the bottom as well. So divide by P divided by Q here, and P divided by Q here. And we get the equation, the derivative of the equilibrium price with respect to the tax rate is equal to price elasticity of demand, price elasticity of supply divided by price elasticity of supply minus price elasticity of demand. Okay, now, apart from my little scribble in this, hopefully we can look back and we can look at this formula and think, what a beautiful formula. Research in economics does not always go quite as well as this. But this is a very nice thing. And through hard work, we've uncovered a kind of very deep connection here. This term here, the derivative of the equilibrium price with respect to the tax rate, that's saying, how does what consumers have to pay change as we increase the tax? So this is called the incidence of the tax. If we can provide a very precise formula and say, well, this incidence of the tax depends on the elasticity of supply for that good and the elasticity of demand for that good. So now we can make very strong predictions. So let me give you a very simple example, e.g., if the elasticity of demand is 0, so that extreme case, remember what we called that? Perfectly inelastic demand, then the rate at which the equilibrium price changes as the tax rate changes is equal to 1, which means every unit of tax we are charging the supplier, the entire unit is being passed on to the consumers. Okay? So here the strategy of, well, let's try and tax the firms because they have far more resources than consumers completely fails, because the equilibrium price simply adjusts so that all of the tax is paid by the consumers. Using our knowledge of elasticities, we've derived a formula that describes the incidence of a tax on consumers. If a tax is charged to firms, how is this tax passed on to consumers? The price that they pay increases, and we know precisely how. It's a formula that relates elasticity of supply and elasticity of demand. For example, if demand for a good is very inelastic, most of the tax gets passed on to consumers. If the demand for that good is very elastic, then most of the tax gets paid by the firms. This is well worth knowing for political and economic reasons. I'd also like to point out at this point that we were only able to derive this deep relationship between taxation and elasticities by hard work, by using some sophisticated mathematical tools and to uncover the connection between these concepts. I don't know how you could do this without mathematical analysis, so hopefully this hints at the power of studying economics in a more mathematical way and being able to make these deep connections and provide clear and precise arguments when you're discussing economic ideas. Anyway, I will see you in the next lecture when we will start consumer theory, which is one of my very favourite topics. See you all soon. Take care.